Hi everybody, my name's Alan Cantle and I'm going to talk about decoupling compute from memory storage in I/O with the Open Memory Interface. And this is an open source hardware initiative. For clarity, when you hear me use the word processor, please take it as meaning CPU and/or accelerator. So as an overview, firstly I'm going to talk about why decouple compute from memory storage in I/O. And then I'm going to take a look at a bit of a step back at a top-down view of systems perspective, where the industry is trending, and also introduce you to some OCP, the Open Compute Project HPC concepts. I actually lead the actual sub-project in high-performance computing. Then I'll give you a basic overview of the Open Memory Interface, and finally I'll bring it all together, seeing how we can decouple compute using the OCP OAM-HPC module with OMI. So without further ado, first section, why decouple compute from memory, storage and I/O? Really, we need to start rethinking computing architecture because the data is at the heart of computing architecture today. Compute is rapidly becoming a commodity. For example, the i386 it would retail today with its number of transistors at around 1 cent. Power efficiency and cost are really today's primary drivers, and that's what we need to focus on. And we need to be able to distribute the compute efficiently. It's not the center of attention anymore. So compute therefore needs one simple interface for easy reuse everywhere. So let's redefine computing architecture. Let's take it back to first principles, and less with a primary focus on power and latency. So in computing, latency is the time taken to move data. More clock cycles equals more latency equals more power. More distance equals more latency equals more power. Hence, power can be seen as a proxy for latency and vice versa. And a focus on power and latency will beget performance, for sure. And we're already seeing this in the heterogeneous processors that have been coming to market for several years now, where they effectively optimize these for specific algorithm types on silicon. But we really need to do this for HPC now, so we need to focus our energy more at the system architecture level. And the silicon level is really taking care of itself to a certain extent. Touching on cache memory, so cache memory is bipolar. It has a bipolar relationship with power, which is our focus now, right? So its implementation really needs rethinking. Cache is very good for power efficiency. It minimizes data movement on repetitively used data. Cache is very bad for power efficiency. Unnecessary cache flashing for data that's touched once or not at all. Many cache layers of cache equals multiple copies burning more power. Conclusion, hardware caching must be efficiently managed at the application level. Now, I'm not going to talk any more about cache, but I would like to ask for you to park your cache religion chip in your brain to one side when thinking about the rest of this presentation. It's an important topic, and we know it can be managed, but it needs to be thought about separately. But I won't go any deeper because I don't have the time. So today, if you're designing a processor, you've got many interface choices from a latency and a power perspective, from memory all the way up to your distant networks over Ethernet, and longer latencies and you burning more power. So your processor designers, they have to decide and allocate beachfront of their processor to each of these interfaces. And the choices are increasing at the moment, making it even tougher decision. And you can live and die by your choices. You may have the best processor architecture in the world, but if you don't choose the right interfaces for a particular application, you find your processor is useless. So this is the way of the world today. So could we simplify this to a shared memory interface? Shared memory has been extremely popular in HPC and the very old days of parallel computing. So could we successfully decouple the processors from the memory and storage in I/O with a shared memory approach? So this is showing you an abstract view of that. So we've got our processor and it's connected to nothing but memory directly with the lowest of latency and the lowest of power. So there's an instant benefit there. And as we reach out to the devices that are further away, we gracefully increase the latency and power and through the shared memory infrastructure. So that would allow processor companies to really focus on their core expertise, and they'll be able to support all domain-specific use cases because they just see everything as one memory interface. And so and as systems designers, we'll be able to actually use these devices for each of our applications effectively. So hopefully that answers the why. So let's take a step back and look at top-down systems perspective, and I want to introduce you to the OCP-HPC concepts as well. So today we're seeing disaggregated racks to hyper-converged chiplets. So, so your classic server is really being pulled in a couple of different directions. And why is that? Well, if we look at the baseline is our classic server, we have physical composability. You can rearrange the devices, remove or add more memory and storage, etc. But in a disaggregated world, it's fully software composable, so none of your resources get stranded as you run different applications. But when you go to the chiplet world, the chiplet world, we really have very expensive physical composability. And I would even argue it's ill-conceived at the moment in the directions I'm seeing the chiplet world go from a composability perspective. From a power baseline, we see that node interconnect is in the 5 to 10 picojoule per bits inside the server. At the rack level, everything's further apart, so we're north of 20 picojoules per bit. And obviously the wonder of the chiplet approach is we're less than a picojoule per bit, which is the attractiveness of chiplets. From a latency perspective, again, you're adding more latency going up and down the rack, and you've got optimal latency in the chiplet. And then from a volume perspective, we've got the volume of the server. You get much bigger volume in your rack scale, and we're sub-cubic inch. So you can see, you wouldn't be remiss in thinking that the hardware people focusing on chiplets don't talk to the software people focused on composability. And I think you'd be absolutely right. And so can we really bring these two together? Is that possible? So it's really being torn apart, as I said there. So can we bring them together? So in the Open Compute project, they have open OCP Accelerator modules, and they use EDSFF interconnect for a new modular approach to attaching memory storage and networking. So I'm going to show you a module here that's been inspired by these standards. And hopefully I'll show you that this can bring the benefits of disaggregation and chiplets together under one modular standard. And you can see here we've got, it would be both software and physically composable. It would be power optimized to around 1 to 2 picojoules per bit, so not too far away from the chiplet world, and much better than the servers. We would still have a good optimal latency, and the module size is considerably less than a server. So I'll expand a little bit more on that. So fully composable compute module, again leveraging the OCP's OAM module, and it's nicknamed OAM-HPC. On the left you can see you still have your big powerful processor on top of this module, and it could even be made up of multiple chiplets as well, so we're not throwing chiplet approaches away. And it has a multitude of interconnect on the bottom for connecting lots of different devices. Taking a closer look at that interconnect, fundamentally we're proposing two different standards at the moment. One, we have 16 of the EDSFF 4C and 4C plus connectors, and we'll have 8 of the near stack connectors. That would give us a total of 320 transceivers for interconnecting from these processors to other devices. And that looks like this module. This one is just an example population. You can mix and match the population. That is the beauty of this approach. But this one's showing 8 E3.S modules. It can be media or memory, and 2 OCP NIC-free network modules, 4 4C cables for cabling to other devices, and 8 near stack cables in this little picture. So really we have a modular, flexible and composable module, and it's protocol agnostic. The hardware, the electrical signals are all fixed, but the protocol is dictated by the processor that gets populated on the module. And obviously some processors talk the same language, some don't. So, but that's important. This is protocol agnostic. The memory, the storage and the I/O is interchangeable depending on the application need. And really your processor must use HBM or have serially attached memory. This does not support parallel DDR memory. But even so, today this module format could support NVIDIA Ampere, Google TPU, IBM Power 10, Xilinx FPGAs, Intel FPGAs, and Graph Core IPU, to name a few. So this is a proposed approach in the OCP-HPC work group. Now, on the memory side, actually memory I/O is finally going serial. There's been many failed attempts over the years, but I think we can say it's moving in that direction now. You can see the OMI DDIMM, Open Memory Interface DDIMM, was introduced in 2019, and an E3 format with 2 OMI channels was proposed in 2020. Smart Modular introduced a Gen Z memory module in 2020, and Samsung just recently announced a CXL.mem memory module in E3 format this year. So I think we can finally say that memory is going serial, so our module approach will clearly be supported by these. Now, just going a bit more specific, let's just pick one of the processors, the IBM Power 10 OCP-HPC module as an example. You can see all the connectors I just showed you on the module surrounding the Power 10. The Power 10 has transceiver attached to everything. So here we can see we're supporting 16 OMI channels with E3.S modules with dual OMI on them. We've got a couple of NVMe SSDs plugged into the other ones in E3 format. We have a NIC.3.0 OCP network card plugged into one of the other modules. And we have a cabled I/O giving you cabling off to some PCI attached device elsewhere. And then we have all the additional cables carrying the SMP and OpenCAPI buses. So this would be the protocol specifics of a Power 10 module that you could then use in this module format. But with this modular approach, so this is that module can be used today with any processor and any protocols and anything, you know, the classic way. But this dense modularity really does bring us a power saving opportunity by leveraging a potentially flexible chiplet level interconnect. So here I'm showing you an X-ray view of the module with the Power 10 on it and the interconnect underneath. And we can measure the Manhattan worst case distances between the die and the chip and the die, the ASIC die on the modules. And we're less than 5 inches worst case. So that really gives us an opportunity to reduce the PHY power to 5 to 10 dB budget and 1 to 2 picojoules per bit. So it's very similar to the extremely short reach standard XSR of the OIF standards. Also, we also have an opportunity to actually get rid of the packaging on these devices and actually use the substrate, use the module substrates as a package, so we get rid of the middleman, so to speak. And that would again increase power integrity and signal integrity further. And this is this approach would is challenging because they're big substrates, but it's not beyond possibility. So we have an opportunity to greatly reduce the power consumption here. Let's take a look at OMI. So the Open Memory Interface, the graph on the right is a log scale graph, and in short it shows you that OMI has a bandwidth of HBM at DDR latency, capacity and cost. So a little bit of a closer, it was introduced in production in 2019. This is not a pipe dream, this is available today and is very robust. But DDR4 and 5 has much lower bandwidth per die area beachfront, not physically composable. HBM is inflexible and expensive and is capacity limited. CXL.mem, OpenCAPI.mem, CSIC, they all have higher latency and they're termed really far memory, not near memory. And similarly, Gen Z is data center level far memory. So OMI is definitely the best serial attached memory approach to take. This is a bit of an eye chart, but I just want to highlight in yellow the memory interface comparisons. It's the ideal processor shared memory interface. The latency is very much on par with DDR, and the bandwidth is almost 10x per area that of DDR. And more importantly, is very similar to HBM. So because it's similar to HBM, that gives us an opportunity for HBM memory with an OMI-enabled logic layer interface. And that would make HBM much more flexible and have capacity options which aren't there today. So OMI should be considered as a logic layer of HBM going forward. This is another eye chart, but I wanted to leave everything for you all to see a bit of detail on the Power 10, but I want to highlight 3 things here. The OMI PHY, you can see it there on the actual Power 10 die. This is all to scale. The latency adder of the PHY channel is actually 2 nanoseconds in each direction. And you can see that it will drive today a 30 dB channel, so it takes 5 picojoules per bit, but there's an opportunity to drop that with the extremely short reach approach. So that's what I wanted to show you there. But here I also want to summarize this and say, let's look at OMI bandwidth versus our single precision flops, because really OMI is helping to address memory bound applications that have been ignored forever. And so here, if we had a maximum reticule size die, we could fit up to theoretically 80 OMI channels on. That would be 5.1 terabytes per second. We know that NVIDIA Ampere's maximum reticule size gives you a 30 single precision teraflops. So, you know, you've got a 6-to-1 there of flops to bandwidth. But as die size shrinks, let's say we shrink it by 7 times the die, the OMI bandwidth reduction is only 2.8, but the flops reduction is 15. So we actually end up with a perfectly balanced 2 teraflops with 2 terabytes per second. So I don't think I've seen anything at decent performance, at least, since the 60s or 70s to that level. So this is really quite interesting that we really are putting more attention on the data here. And we have plenty of capacity behind OMI that you don't have on HBM. So pulling all this together, let's see if we can build a decoupling the compute really truly with the OAM-HPC and OMI. So here I'm going to look at 1, 2, and 3 port shared memory buffer chiplets that we could create, and I'm going to show it in this module format. So the green box represents the OAM-HPC module, and we've populated a maximum reticule size processor with its 80 OMI XSR channels. Let's firstly add an OCP NIC 3.0 card with an OMI 3-port buffer chiplet on board. So we've got 1 port going to the main big processor. We've got another port which may interface to maybe a little acceleration processor chiplet. So you've got a 2nd port into that memory. And then we've got the 3rd port that would give us our fabric expansion to OpenCAPI, CXL, Gen Z, Ethernet, InfiniBand, etc. So that could be implemented in NIC 3.0. In an E3.S module, we could have a 1 or a 2 port buffer doing something similar, the same. You know, you've got the main port to the processor. The 2nd port could be to an accelerator. Actually this time buried in the buffer if that made sense to do so, and a little tiny accelerator. So that's another approach. As I mentioned, the HBMs, we could have a couple of HBMs attached using 8 of the OMI channels to give the same performance as HBM today, and so that would be a composable option. From an interconnect perspective, we could use a near stack, and we could put a 2-port OMI buffer chiplet on there to convert to the fabric standard of choice. And here you'd have the shared memory, a small amount of shared memory inside the buffer. So you don't need the external memory for this, but it's still the same shared memory approach. Or we could take the EDSF cabled connectors, and actually with those, we can actually populate that 2-port buffer, the same 2-port buffer, inside the connector itself. So we actually have a protocol specific active fabric cable. So imagine that you could plug a CXL cable in to plug to a CXL device, or an OpenCAPI cable in to plug to an OpenCAPI device, etc. This would be truly flexible with this approach. And finally, you could also, if you needed an OMI attached memory, but it wasn't directly local to this module, you could go for a medium reach extender buffer with less than 500 picoseconds of round trip delay adder to actually reach further away OMI memory. So hopefully this gives you an understanding of one memory interface where we truly have decoupled the compute from memory storage and I/O. So once we have this module though, how do we use it? So the OAM modules actually plug into the OCP Accelerator infrastructure. So you can see free chassis from Inspur, Hive and ZT systems. These are real and they're being upgraded today to OAM version 2. They support 8 modules. So we can similarly support 8 of the modules I just shown you in that same free use chassis and plug into the OCP ecosystem. The only difference is there is no motherboard. These would just mate to a water-cooled cold plate and also bring the power in through that cold plate. So and this would then plug into that OAI chassis. So in summary, we want to redefine computing architecture with a focus on power and latency. And we want that to be a shared memory-centric architecture. We can leverage the open memory interface for this, and we can use this dense OCP modular platform approach to actually turn it into a practical reality. So are you interested? If so, how to get involved? From silicon startups to open hardware enthusiasts alike, I would encourage you to look at these steps we're taking. Firstly, join the OpenCAPI Consortium or the OCP-HPC subproject. Replace your DDR memory with standard OMI memory interfaces on your next processor design if you're designing your own processor. Add a couple of low power OMI PHYs with this new XSR interface on any spare beachfront you may have on your processors so we can start to enable this transition to a completely decoupled compute from memory storage and I/O. Build OAM-HPC modules around your large processor devices. Help the community build specific 2 and 3 port OMI chiplet buffers to go out to different fabrics like CXL or OpenCAPI, etc. And help the community to build OMI buffer enabled E3.S and NIC 3.0 modules as well. So I think we're already well underway with a lot of the efforts here, and bringing a wider community together will be great. So thank you very much. Any questions? And there's some links to the OpenCAPI Consortium and the OCP-HPC subproject. Thank you very much.
Thank you very much, Alan. So